At this point, we'll now attempt a more complicated block diagram reduction example. Specifically, we're going to look at this block diagram, which represents the torque control of a DC motor. So looking at the components, what we have here is we have a controller, which is a PI controller. It's based on an error. It creates a control output, which in this case is the armature voltage, where the output is proportional to the error. So it's the error times a constant Kp, and it's also proportional to the integral of the error, where 1 divided by S is integration. So we haven't spoken a lot about PI control yet, but there's an example. Here then is the dynamics of the motor. We have some electrical dynamics where the output is the armature current. That is what we're using for our feedback for our control. We're doing torque control, but the fact that torque is proportional to armature current when we have an armature controlled DC motor, it turns out that it's easier to measure current than it is to measure torque. So that's why we're going to use current for feedback and apply a command of desired armature current. We also have the mechanical dynamics of the motor, where there's another feedback loop that's due to the natural dynamics of the motor and its back EMF. And so what we want to do is we want to reduce this whole thing down into a single transfer function so that we can see what the poles of this whole system is. And if we can express the poles for this entire system, then we can see how the control gains Kp and Ki can be designed to put the poles where we want them. This appears quite complicated, and so the way that we're going to reduce it is to really go step by step. And we're going to apply approach number 2, employing the different sort of rules that we've memorized. So take a look and see if there are any places where we can very quickly and simply apply some of the rules we know to begin to reduce this block diagram. So one place that we can see is that we have these two blocks that are in parallel to one another. And so very quickly we can reduce those two, where we recall that blocks in parallel sum. So we have the one block Kp, we have the other block Ki divided by S. They simply add together. Then over here we have these two blocks in series. And so again, very simply we can reduce this by recalling that blocks in series multiply. So we multiply K. By that transfer function we get K divided by the quantity Js plus B. Moving to the next slide, we've replaced the two blocks that were in series and the two blocks that were in parallel, and already we've started to make the block diagram simpler. If we look closer, we can see a couple more structures that we may recognize. In particular, we have two feedback loops, two negative feedback loops that we recognize, and we know how to reduce those. The problem that we have is that these two feedback loops are sort of intertwined, and so what we need to do is unwind them. Specifically, I want to take this feedback loop and I want to get it inside of this other feedback loop. So I want to move this summing junction to the other side of that block. And the way to do that, or the way that we're going to sort of justify this, is to think about sort of what the signals are equal to in this block diagram. So I'm going to imagine that the signal going into that first block has the name A. And so the output of that block is simply the input multiplied by the transfer function. So that's what this signal is equal to. The original system has a branching point here, and so this signal is also equal to A times K divided by JS plus B. And it goes through this transfer function, and so the output again is simply the product. So I multiply KB times the input signal, and I get that output. And so what I want to do is I want to rearrange the block diagram. I want to move this branching point, but I want to keep sort of the output the same. So I want to keep this signal still equal to this. So I don't want to change fundamentally what the output of the block diagram is. I just want to rearrange it. So when I move this, it's now as if I'm branching off from A and putting it through this block. And so if I left the block as it were, the output would simply be A times KB. But that's not the output that we need. We need this full thing. So we actually need to add this whole element to that block. In other words, the dynamics that we skipped by moving the branching point now need to be added to this block. Okay. So if I do that, I get something that looks like this. So I moved that signal over here, and so the dynamics I skipped, I need to add to that block. So this is still there, but I've added these dynamics to that KB. When I move this branching point to here, however, I'm still not completely unwound. What I need to do is I need to swap those two branching points. And so now the question is, does the order of branching matter? So let's real quickly think about this. So I have this signal A, and I have one branch off, and I have another branch off. Since they're both branching from this signal A, they're both equal to A. If I swap these, does that fundamentally change anything? And the answer is no, because no matter where I branch off this signal, they're still going to be equal to A. So whether I branch off here or branch off here, the outputs are going to be unchanged, which is what I want. So the order of branching does not matter, and this block diagram is equivalent to this block diagram, and we've achieved our goal of unwinding these two feedback loops. Looking at this, in essence, we've sort of created a rule that when we move a branching point to the other side of a block, we need to add those dynamics. And so this sort of rule can be found on page 495 of the book. And there are other rules. So instead of moving the branching point from the output to the input, what if I had moved a branching point from the input to the output? What would I have to do? Or what if I moved a summing junction to the other side of a block? And so this table has those rules. In general, I don't rely on such a table. In general, what I do is I just try and think through what the behavior of the system is. So I do this sort of logic where I create a signal and I look at what the output is, and when I make my change, what do I need to do in order to keep the output the same as it was? Another question, which we haven't answered yet, is does the ordering of summing points matter? And so we're not going to swap any summing junctions in this example, but we'll go ahead and address it real quickly. So let's imagine that we have some input signal A, and we're subtracting off a signal B, and then we're adding a signal C. Okay. And so looking at this, the output of this is going to be determined as follows. So the first summing junction has A coming in on a positive input and B coming in on a negative input. So the output is simply A minus B. And then that signal A minus B is added to the signal C. So the complete output is then just simply A minus B plus C. And what if I switch the order of the summing junctions such that I still have my A signal, but instead of subtracting B first, I add C, and then I subtract B. So, did changing the order of those summing junctions change the output? So let's take a look. So the first summing junction has an A coming in on a positive input and a C coming on a positive input. So the output is just A plus C. And then that signal has a signal B subtracted from it. So then we have A plus C minus B. And so looking at that, we've got the same signals with the same signs. It's just that the order of the addition and the subtraction changed. It turns out that that doesn't matter. These are exactly equivalent. It doesn't matter, 5 plus 4 is the same thing as 4 plus 5. So just as the order of branching didn't matter, the order of summing doesn't matter either. So returning to our example, we've now reduced our block diagram to this point. Looking at this, we now again see some structures that we recognize as being standard structures that we know rules for reducing. In particular, we have this negative feedback loop, and we have these two blocks in series. So again, blocks in series simply multiply. So we have the transfer function k divided by js plus b multiplying 1 times s, 1 divided by s, so that series of two blocks can be replaced by the equivalent. Here we have a negative feedback loop, and so again think about what the rule for that is. Well, the rule that we use is forward over 1 plus loop. So if this is our input and this is our output, and we look at the negative feedback loop, the forward path has just this block in it. So the forward path is 1 divided by RA plus SLA, and then the denominator is 1 plus loop, where the loop includes both of those elements. So it's as if those two blocks are in series, where two blocks in series simply multiply. So we get KB times K divided by RA plus SLA times the quantity JS plus B. So that's what that reduces to. This is a little messy. We'd like to clean it up. We'd like to reduce it to the form such that it's a single polynomial divided by a single polynomial. So we want to clear out the fractions. The way that we clear out the fractions is by multiplying on the top and the bottom by the denominator of the fractions. So if we multiply on the top and the bottom by this, and I multiply here, the RA plus SLA will cancel, and we'll be left with a JS plus B. When we multiply this quantity by the denominator, it'll cancel, and we'll just be left with a KB plus a KB times K. And when we multiply this by the denominator, it'll also distribute to the 1. So we'll also end up with RA plus SLA JS plus B. So that's what that piece of the block diagram reduces to. Going to the next slide, that reduction, that block is the negative feedback loop, and this block is the two that were in series. Then we continue on, and so looking again, we find another negative feedback loop which we can replace using the rule forward over 1 plus loop. I won't go through the algebra, but if we do, this is what results. We then have these two blocks in series. Again, blocks in series multiply, and we get to the final transfer function. So we've taken that very complicated block diagram at the beginning and reduced it down to a single transfer function so that we can see exactly what the poles of the transfer function are. And we can see what the effect of each parameter is on the poles. What the effect is of the control gains, Kp and Ki, or even what the effect is of the various parameters of the motor, the friction, the inertia, the inductance, the resistance, etc. Okay. Let's now take a look at block diagrams with multiple inputs. And so this is something that we've alluded to and we've discussed sort of conceptually, but how do we handle that sort of when we do our analysis? So in this case, we've got a single output Y, and we've got two inputs. We have our reference, our command, but we also have this undesired input due to the disturbance. And so it turns out for linear systems, when we have multiple inputs, the total response is simply the sum of the individual contributions. This is called the property of superposition. And so sort of conceptually, this allows us to assume only one input is non-zero at a time. So for example, if I want to look at how does the system respond to the reference R, I can treat D as not being there. So I can treat D as 0. And so if I put some input R, I can look at what the response is at Y. I can then ignore R and look at what the response due to D is. So I can treat R as 0. I can look at some input D, and I can look at what the response is of the output. If I were to apply both of these signals at the same time, it turns out that the output is simply the sum of the response due to the inputs individually. So if R and D are applied simultaneously, then Y is simply the response when we had R by itself and D by itself summed together. And this is a very powerful and helpful property, this property of superposition. But one thing that you need to keep in mind is that it only applies to linear systems. So again, this is a reason why we like linear models. Okay, so let's go ahead and take a look at this example. Try and determine what the output is for a simultaneous application of R and D. So as was stated, we'll look at each input one at a time. So we'll ignore D and look at what the response is due to R. And so this negative feedback loop is something we're familiar with, where the transfer function can, from R to Y is simply forward over 1 plus loop. And in this case, the forward path includes C, GA, and P in series, so that becomes our numerator. And then our denominator is 1 plus loop, where the loop is these 4 blocks in series. It includes C, GA, P, and GS in series. And so that's what our transfer function is for an input of R and an output of Y. We can apply a similar process to determining the response due to the disturbance. So we ignore R, treat it as if it were equal to 0, and we look at the response of Y due to an input D. And this may be a little confusing, but even though D sort of enters into a different location of the block diagram, we still have this negative feedback loop. We still have a feedback signal that's being subtracted. And so we can still use our rule forward over 1 plus loop, where in this case D is our input and Y is our output. So if we go from D to Y, the only element in the forward path is P. So that's going to become our numerator. But our feedback loop, the loop part, is exactly the same as it was when we looked at R. So applying that rule, P is the forward path, and our loop is the same loop as we had in both cases. Okay. If you have a little bit of trouble believing this rule when we have D as an input, I'll try and justify it to you a little bit better on the next slide. But now the question is, if this is how the system responds to R and this is how the system responds to D, how does this system respond to both simultaneously? So if we were looking at R all by itself, the output would simply be the transfer function times the input. And if we were looking at this response of the system to D by itself, the output would simply be the transfer function times the input D. If we're to apply both simultaneously, we can apply the property of superposition where the responses simply add. So we have the response due to the input R, and we simply add it to the response due to the input D to give us our total response. And moving to the next slide, I'm going to try and justify to you why we can still use our forward over 1 plus loop rule even though D enters in a different location. So some people may look at this and think it's as if we have a positive feedback system. It's as if this is the input and then we have this feedback loop where we add the feedback signal. And so that's true. We can think of it that way. But the thing is, we still have this negative summing junction where we're treating R as if it were equal to 0. And so when we have this signal and we subtract this signal, subtracting something from 0 is sort of the same as multiplying it by -1. So 0 minus 1 is the same as taking 1 and multiplying it by a -1. And so we're replacing this summing junction where we're subtracting from 0 with this multiplication by a -1. And so these two are equivalent, where here we're thinking of the system as positive feedback. If you recall, the rule for positive feedback is forward over 1 minus loop. And in this case, the forward path is simply P. The feedback or loop includes P, GS, -1, C, and GA. And so since they're all in series, we just multiply them. When we're subtracting a negative number, that becomes positive, and this is the same thing we predicted on the previous slide, where it's still forward over 1 plus loop because it's still a negative feedback system.